Welcome back. And in the second part of this series, you've learned about bond breaking, bond making. So energy is required to break the bonds, and then energy is released when the bonds are released. And in fact, this is something that we can draw in a diagram. Okay, so these are the diagrams, the finished diagrams. Okay, so this is for an endothermic reaction. Okay, this is for an exothermic reaction. So let's see what happens. In both the reactions, you've got your reactants, okay? And you're gonna have the bond breaking. So bond breaking is always going to be endothermic. It always requires energy. So we're going to go up in energy. You can say that the excess is the potential energy. So we're going to go up in energy. So this is bond breaking. Okay? Then you are going to go into the bond making. Now, depending on whether you're gonna have more energy released than absorbed in the reaction, your reaction is gonna be either endothermic or exothermic. So in this case, you have the products here and products there. And in the endothermic reaction, you required a lot more energy. Okay, you required a lot more energy to break the bonds than you released when making the bonds. On the other hand, in the exothermic, you released more energy than what was required to break the bonds. Therefore, you would have an exothermic reaction. Now, here it's very important to realize that whenever we find any value in the bond breaking, bond making situation, is going to be this delta H sign here. Okay? Why? Because this value is actually going to be the value of the energy change of the reaction. Okay? The activation energy, which is this value here, okay, activation energy is going to be the energy needed to break the bonds. So let's write it. EA equals activation energy, and this is the energy needed to break bonds. Okay, so that is very important, and that is the reaction, the energy needed to start the reaction. Okay, remember, to start the reaction, we will always need to break the bonds. Okay, now, apart from this, okay, you also have a position up here that is called a transition state. Okay, now, because we've done the mechanisms, let's actually see what happens when you have an alkene, okay, instead of an alkene. Let's do a halogene alkene, okay? So a primary halogene alkene, okay? And we're gonna react it with a nucleophile. And we've always said that this is called a transition state. And the product would then be this one plus the Br minus. So this is a transition state. something that you cannot extract. Okay, now this is something that is going to be very important when drawing a energy diagram. Okay, so if we were to draw the energy diagram for this reaction, okay, let's actually okay, I would highly always advise energy, write the excess, and time. Now time is time or progress of reaction doesn't really matter. So in this reaction, let's assume that this reaction was an exothermic reaction. Okay, now substitution reactions can be either exothermic or endothermic depending on the reactant. Okay, so you can't really know whether something is exothermic or endothermic prior to the reaction. Though, for example, if you have something like electrophilic addition, not normally, that is always exothermic because of the type of reaction. But here you can't really say that, okay? You either need to know the values beforehand, okay? Or otherwise you would not be able to say, okay, this is going to be a specific value, okay? You can't say that, you can't do that. So here we have the reactants. We will go up in energy because of the bond breaking. And then we said it's exothermic, so we're gonna go down. So these are the reactants and the products. Okay, so what we'll have here would be the transition state. Okay, Ts equals transition state. Now, this is the activation energy, and this value here would be the enthalpy change. Okay, one last thing you might need to know about this is the catalysts. What happens when you use a catalyst? Okay, when a catalyst is added, all you would have is the same reaction, but the catalyst gives a different energy pathway. This energy pathway is normally going to be lower in energy than the uncatalyzed reaction. Remember, the catalyst will make the reaction go faster, okay, without it being changed at the end of the reaction. And that at the end of the reaction is very important because it means that during the reaction, it can participate, but it is regenerated at the end of the reaction. So now what you'll see is that you have a reaction pathway that is going to be lower in energy. The activation energy will be lower in energy than without the catalyst. Okay, so it's the same thing, but you will draw a curve. Okay, you will draw the hill, okay, the energy hill that is required for the reaction to be lower than the previous activation energy. Now, with regards to this, we can stop here. During our next lesson, we're going to be speaking about Hess's cycles. Okay, and if you need any questions, please either leave a comment or just send me a message. Okay, thank you.